So this method can be extended in a fairly natural way to Katz back-off models for the trigram case. So we're now going to define an estimate of Wi given two previous words. And this is derived in a very similar way to the bigram case. So again, I'm going to define sets A and B, which now depend on the two words being conditioned on. So this first set A is the set of words W such that the trigram count is greater than 0. And the second set B is the set of words W such that the trigram count is equal to 0. So if we look at this Backtoff estimate, the first case is as follows. If we come across some word Wi such that the trigram count is greater than 0, we take the ratio of the discounted count minus the count. And so this, again, is going to be something like count of the trigram minus some constant, say 0.5. And this is simply the count of the bigram being conditioned on. Now again, this definition gives us some missing probability mass, and we have an expression for that missing mass down here. So alpha of Wi minus 2, Wi minus 1 is going to be 1 minus. Now again, I have a sum over all words whose count is greater than 0, and I have this estimator I showed you, count star divided by count. So this is the missing probability mass. And again, for any word which is seen in the set B, i.e. for which this count is equal to 0, we define the Backtoff estimate in the following way. We're again going to split this missing mass between these words in the set B, and now we're going to split this in proportion to the Backtoff estimate at the bigram level. So this is just the estimator I showed you on the previous slide. We essentially have a recursive estimate here where we're going to look at the Backtoff estimate at the level below, at the bigram level. So here on the numerator I have that Backtoff estimate, and down here I have a normalization term where I sum over all words in B, and I have that Backtoff term here. So this is simply taking the missing probability mass alpha and splitting it in proportion to these Backtoff estimates at the bigram level. So that's essentially it. That is a trigram Backtoff method. The one parameter in this approach is this value, say 0.5, that I'm using in discounting. This is the value that I subtract from a count to form this discounted count. And so this will be typically some value between 0 and 1. And one way to choose this value is, again, by optimization on validation data. So you can test a series of values between 0 and 1. For each one, see how well the language model performs on this validation set of data, and pick the discount value which gives you the best performance on that validation data. A value of 0.5 wouldn't be untypical. It's usually somewhere around there.